Hello, Assalamualaikum. So, in this class, we'll be dealing with the few numericals of the simple gas turbine engine. But before that, we have to take into account the compressor and the turbine efficiency. And for this, we have plotted the TS diagram. As you can see here on the TS diagram, we have plotted the process of the compression in the compressor from state 1 to state 2. Okay. So this state 1 represents the static state and the state 01 is going to represent the stagnation state. Similarly for the state 2 it shows the static state, and for the stagnation state it is represented by 02. And as you can see here, these are the lines for the constant pressure, and along this constant pressure line the isentropic state and the actual state are plotted. For the actual state, the temperature raise is higher as compared to the isentropic state. Similarly, for the stagnation state, the stagnation states are located along the constant pressure line represented by P02, and the stagnation state for the actual state are represented by 02, and the isentropic stagnation states are represented are by 02 dash. So this dash is going to represent the isentropic state. On the right hand side we have the c square by 2cp, where c is the velocity, and you can say v square by 2cp is going to represent the dynamic component for the state 2, and c1 square by 2cp is going to represent the dynamic pressure or the dynamic temperature, as you can say here, for the state 1. Okay. So during the compression process, the compression is done in order to increase the pressure from state 1 to state P2. Isentropically, there is no change in the entropy. So moving from state 1 to state 2 dash, but in the case of the actual process, the lines are represented by these dotted lines. So the state will appear at a point represented by 2, which is located at the state higher than 2 dash, because there is a change in entropy. As a result, the raise of the temperature in the actual process is actually higher than as compared to the isentropic process. Similarly, the stagnation state for the isentropic one is represented along this vertical line. If you are going to extend this 2 dash to 02 dash, so this will give you the isentropic stagnation state. And from state 2, if you are going to scratch this vertical line, so this will give you the actual isentropic state, which is 02. Okay. So whenever we are going to define the efficiency of the compressor or the efficiency of the turbine, we are going to define in terms of the actual work done or the ideal work done. In terms of actual work done or the ideal work done. So now let's define the compressor and the turbine efficiency. We are going to first discuss the isentropic efficiency, and then we will discuss with the polytropic efficiency. So for the isentropic efficiency for the compressor, we know the compressor is going to consume the work. As a result, the compressor efficiency is given as isentropic work done divided by the actual work consumed. Isentropic work consumed divided by the actual work consumed. So isentropic work consumed can be written in terms of the enthalpy as the change in the stagnation enthalpy isentropically divided by the change in the stagnation enthalpy actually. So this is the ratio of the isentropic work consumed divided by the actual work consumed. So in actually, the work consumed will be higher because of the increase in the entropy, and isentropically the amount of the work consumed by the compressor is actually lower. So we can define the compressor efficiency is the ratio of the isentropic work consumed divided by the actual work consumed. Now we can replace the delta H naught in terms of the temperature. Cp and Cp are get cancelled out. So the compressor efficiency can be written in terms of the stagnation state, that is T02 dash minus T01 divided by T02 minus T01. And similarly for the turbine we can write that the turbine efficiency is the ratio of the actual work done by the isentropic work done. So because of the irreversibilities present in the gas turbine components, the amount of the work delivered by the turbine is actually lower than the amount of the work produced by the turbine asentropically. So we can write the turbine efficiency as W by W dash. So W is going to represent the actual work done by the turbine, and W dash is going to represent the isentropic work done by the turbine. So this actual work done is T03 minus T04 if you are going to consider the expansion from state 3 to state 4, and for the isentropic one you can write T03 minus T04 dash. Okay. Now while performing the cycle calculations, the compressor efficiency and the turbine efficiency will be assumed, and the temperature equivalent of the work transfer for the given pressure ratios are given as, we can write the actual raise in the stagnation temperature from state 1 to state 2 can be written as T02 minus T01 1 hour compressor efficiency times T02 dash minus T01, and we can now replace T02 dash by T01 in terms of the pressure ratio. Taking T01 as a common, so you will be left with T01 by compressor efficiency times T02 dash by T01 minus 1. So now we can replace T02 dash by T01 as P02 by P01, because this dash state is going to represent the isentropic temperature. So isentropic expressions are can be written for the pressure ratio in terms of the temperature ratio, which is P2 T2. If you recall from the isentropic expression, you can write the temperature in terms of the pressure ratio as well as the pressure ratio in terms of the temperature ratio. So we can now write T02 dash by T01 as P02 by P01 raised to power gamma minus 1 by gamma. And similarly you can write it the net stagnation temperature decrease for the turbine can be written as efficiency of the turbine T03 into 1 minus 1 over P03 by P04 raised to power gamma minus 1 by gamma. The next is the polytropic efficiency. Now in order to understand the concept of the polytropic efficiency, it is very convenient to understand the TS diagram that is plotted here. As you can see here, the TS diagram is plotted and it is going to represent the stage efficiency with respect to the compressor efficiency. Remember, here we are going to take into account the compression into the number of the stages. Okay, so let's say starting from this point and ending up to this point isentropically, when the compression is to be done, let's say from this state to this final state. Okay, so consider this as a single stage. So we are going to take into account the net raise in the temperature isentropically is represented by delta T dash. But if the compressor is divided into the number of the stages, so for all the constant pressure lines we can plot a particular stage and assume that this is one stage that is represented by delta T dash S, that is going to represent the net change or the net increase in the temperature isentropically for a particular stage is represented by delta T dash S, and delta T S is going to represent the actual raise in the temperature for the stage. Okay, and this delta T is going to represent the actual change in the temperature raise for all the number of the stages. Okay, now from the concept of the efficiency of the compressor, so if you are going to write the stage efficiency, what is the stage efficiency for the compressor? If you recall the previous efficiency definition, we said that the compressor efficiency can be written as isentropic work done divided by the actual work consumed. Isentropic work consumed divided by the actual work consumed. So in terms of the isentropic temperature increase in a particular stage is given as delta T dash S. This is the isentropic increase in temperature, okay, for a particular stage, and the actual increase in the temperature for a particular stage is delta T S. If we are going to define the efficiency of the stage, okay, for all the number of the stages, so we can say the delta sum of the all the number of the stages, the actual change in the temperature can be written as summation of delta T S dash divided stage efficiency. So as far as the TS diagram plotted here, it is very important that you must understand the delta T terms which are written here. So first of all, this S subscript which is written here, this is going to represent the stage, and this dash is going to represent the isentropic. So we have the isentropic increase in temperature for a particular stage is represented by this vertical distance, and we have the delta Ts is going to represent the actual raise in the temperature for a particular stage, and it is represented by this vertical distance, and this delta T is going to represent the overall raise in the temperature for all the number of the stages, and this delta T dash is going to represent the raise in temperature isentropically for all the stages. Okay, so from the definition of the efficiency of the compressor, we can write delta T is equal to summation of delta T dash S divided by the efficiency of all the stages. So this will become equal to 1 over efficiency of the stage times overall change in the temperature, or the overall raise in the temperature for all the number of the stages isentropically. But from the definition of the compressor efficiency, we know the actual change in the temperature can be written as the ideal change in temperature isentropically divided by compressor efficiency. So we can now relate these two expressions, that is the actual change in temperature for a particular stage in terms of the stage efficiency, can now be related to the compressor efficiency. So this delta T term and this delta T term both are equal, so we can write, so this Ns by Nc is equal to overall raise in the temperature isentropically for all the number of stages divided by the overall raise in temperature. For the polytropic compressor efficiency can be written as in the differential form dt dash by dt is equal to constant, and from the isentropic process we know T by P raised to power gamma minus 1 by gamma is constant for the isentropic process, which in differential form can be written as dt dash by T is equal to gamma minus 1 by gamma dP by P. Now substituting the value of dt dash from the above equation, we can replace the dt dash as efficiency, polytropic efficiency of the compressor, dt by T equal to gamma minus 1 by gamma dP by P. Between the inlet and the outlet, So polytropic efficiency is constant by the definition. So this polytropic efficiency will become equal to log of P2 by P1 rest for gamma minus 1 by gamma divided by log of T2 by T1. Now this equation enables us to calculate the polytropic efficiency of the compressor in terms of the pressure and temperature. So this equation can be written as equation 2.14 can be written as such a way that we are going to express the T2 by T1 as P2 by P1 raised to power gamma minus 1 by gamma multiplied by the polytropic efficiency of the compressor. And finally, the relation between polytropic efficiency of the compressor and the compressor can be written as T2 dash minus T1 divided by T2 minus T1. So if you take T1 as common, so T1 for the numerator and the denominator side will be cancelled out, and you will have T2 dash by T1 minus 1 divided by T2 by T1 minus 1. So this dash is going to represent the isentropic state. So we can replace this temperature ratio in terms of the pressure ratio isentropically, which is P2 by P1 raised to power gamma minus 1 by gamma minus 1 divided by T2 by T1 can be replaced as P2 by P1 raised to power gamma minus 1 by gamma times polytropic efficiency minus 1. Okay. Now we can write gamma minus 1 by gamma times polytropic efficiency in this form, which is n minus 1 by n. Okay. So this is the more familiar expression for the polytropic process, and from the definition of the polytropic efficiency we can now write the T3 by T4. Similarly for the turbine side we can write, which is T3 by T4 will become equal to P3 by P4 multiplied by the polytropic efficiency of the turbine times gamma minus 1 by gamma. And similarly, as we have written the expression for the compressor efficiency and related it with respect to the polytropic efficiency, we can now relate the turbine efficiency with respect to the polytropic efficiency of the turbine, which is Nt is equal to 1 minus 1 over P3 by P4 raised to power polytropic efficiency of the turbine times gamma minus 1 by gamma divided by 1 minus 1 over P3 by P4 raised to power gamma minus 1 by gamma. So we have plotted the isentropic efficiency on the y-axis, and on the x-axis we have plotted the pressure ratio. Okay. So as you can see here, for the higher pressure ratio we have the higher isentropic efficiency of the turbine. Now if you recall the expression, which is T02 minus T01, which is equal to T01, so this compressor efficiency is now written in terms of the polytropic efficiency in this form, which is P02 by P01 raised to power n minus 1 by n minus 1, where n minus 1 by n is equal to gamma minus 1 by gamma times the polytropic efficiency of the compressor. Okay. Similarly for the turbine, the delta T from state 3 to state 4 can be written as T03 times 1 minus 1 over P03 by P04 raised to power n minus 1 by n. Okay. Where n minus 1 by n for the turbine is equal to the polytropic efficiency of the turbine times gamma minus 1 by gamma. Now we are going to take into account the effectiveness of the heat exchanger. So as you have seen from the diagram, the effectiveness of the heat exchanger can be defined as the actual heat transfer by the maximum possible heat transfer. So this can be expressed in terms of T05 minus T02 divided by T04 minus T02. The exhaust gases from the turbine reject the heat at the rate of m dot cpg. So this g is going to represent for the gases. So the rate at which the heat is to be rejected from the gases after exiting from the turbine is m dot cpg T04 minus T06, and while the compressor delivery air receives heat at the rate of m dot cpa, where a is going to represent for the air, so m dot is the mass flow rate, so m dot cpa times T05 minus T02. And for the energy conservation, we assume the mass flow rate entering into the compressor and the turbine are equal. So we can say for the effectiveness of the heat exchanger, whatever the amount of the heat which is lost by the hot fluid is actually the amount of the heat which is gained by the cold fluid. Okay. Both the T05 and T06 are unknown, so we need to have another parameter, that is the efficiency. The efficiency is given in terms of the effectiveness, which is actually transferred by the maximum possible heat transfer. In the heat exchanger, there are also pressure losses. So the P03 stagnation pressure at the state 3, it can be written as P02 minus the change in the back pressure. That is this pressure loss has to be taken into account minus delta PHM. So this pressure loss before the heat exchanger and in the combustion chamber. Okay. And P04 is minus PA is equal to the pressure loss at the gas side, and P03 is equal to P02 times 1 minus delta PB by P02 minus delta PHA by P0. Another important fact which is shown here, as you can see here, the CP is going to change as the temperature is going to change, and also the fuel air ratio is changing with the temperature is going to change. Okay, so this curve will be used later in the solving the numerical particular, and specific heat capacity for the air side, it can be taken as 1.005 kilojoule per kg into Kelvin, and gamma for the air is 1.40. So this factor gamma or gamma minus 1 becomes 3.5. And for the combustion gases, the specific heat capacity for the gases, it is equal to 1.148 kilojoule per kg into Kelvin. Gamma for the gases, it can be taken as 1.33. So this factor gamma or gamma minus 1 would come out to become 4. Okay. Now the next is the graph between the fuel air ratio versus the raise in the combustion chamber temperature. So on the y-axis we have the combustion temperature raise, and on the x-axis we have the fuel air ratio. Okay, so this is also the graph which we will be using in solving the particular numerical. So if you have the higher raise in the combustion temperature, okay, so we can have the higher fuel air ratio required. Okay, let's see at this curve which is 800. So for the inlet temperature raised to 300, 400, 500, 600, 700, at 800 here, we have the fuel air ratio required is roughly around 0.011. Okay, so if the combustion temperature raise is lower, then also the fuel air ratio becomes lower too. Here we have defined the combustion efficiency, which is the theoretical fuel air ratio for the given increase in the temperature divided by actual fuel air ratio for the given increase in the temperature in the combustion chamber. The next is the specific fuel consumption air fuel ratio divided by the net work done, and the net work done in kilowatt hour per kg per second for the air flow. So you can express this in terms of the fuel air ratio, which is 3600 times fuel air ratio divided by the net.
A free turbine, sometimes called a free power turbine, is a turbine which is not connected to the compressor. It's connected only either to the propeller or to the rotor reduction gearbox. The fact that it's not connected to a compressor allows a free power turbine to seek its own optimum design speed, rather than that of a compressor. The free power turbine has further advantages. The propeller of a free power turbine engine can be held at low RPM during taxiing, thereby reducing noise pollution and wear on the brakes. A free power turbine engine requires less starting torque than does an engine where the turbines and compressors are coupled together. A rotor parking brake can be fitted to an engine with a free power turbine. This eliminates the dangers inherent in having propellers rotating in windy conditions on the ground. The power output of a turbine can be increased by increasing its diameter. But this would have two detrimental effects. Firstly, it would increase the drag factor by requiring that the engine be designed to have a large diameter. And secondly, that greater stresses would be imposed because of the greater centrifugal forces created. A more effective method is illustrated in this picture, where an increase in the number of stages which comprise the turbine allows an increase in power output with a reduction in turbine diameter. It's a fact that the efficiency of a turbine blade increases as its rotational speed increases. The losses reduce in proportion to the square of the mean blade speed. Unfortunately, the stresses on the blade increase in proportion to the square of the blade speed. It would seem then that the engine designer is locked into a vicious circle, where any attempt to increase engine efficiency by increasing turbine speed would require stronger blades. This would mean making them heavier, which would create greater stresses on them, and so on ad nauseum. All is not lost, however. The advent of the high-ratio bypass engine, with its much greater propulsive efficiency, means that for a given thrust it can have a smaller diameter turbine. This, to some extent, circumvents the vicious circle problems mentioned previously. The high bypass ratio type of engine shown here consists of three spools. Firstly, we have the high-pressure spool, driven by the high-pressure turbine, which rotates the high-pressure spool at relatively high speeds. Then, to the rear of the high-pressure turbine is the intermediate pressure, or IP turbine, driving the intermediate pressure compressor through a shaft which spins inside that of the high-pressure turbine. Finally, the rearmost turbine is the low-pressure, or LP turbine. It drives the low-pressure compressor, more commonly called the fan, through a shaft which runs inside the high-pressure and the intermediate pressure shafts. Nozzle guide vanes are of aerofoil shape. The space between two nozzle guide vanes forms a convergent duct. Within this convergent duct, some of the potential or pressure energy in the gas stream is converted to kinetic or velocity energy. The turbine blades themselves can be impulse type, which is similar in action to a water wheel, reaction type. These blades rotate as a reaction to the lift they create as the gas stream flows over them, or a mixture of the two types, which is called impulse reaction. This picture shows three end-on views of the combination impulse reaction blade. It illustrates how the shape of the blade changes from its base to its tip. The shape change is accomplished by the blade having a greater stagger angle at its tip than at its base. This gives the blade a twist, which ensures that the gas flow does equal work along the length of the blade, and also enables the gas flow to enter the exhaust system with a uniform axial velocity. Normally, gas turbine engines do not use either the pure impulse or the pure reaction type of blades. The proportion of each type of blade utilized is dependent upon the design requirements of the engine. In general, the combination impulse reaction is more commonly used. Impulse-type turbine blades are used in air starter motors. It's very rare to find pure reaction blades being used. When they are, the nozzle guide vanes are designed to divert the gas flow direction without altering the pressure of the gas. The considerable stress imposed upon the turbine blade and the turbine disc when the engine is rotating at working speed makes the method of fixing the blade to the disc extremely important. The fir tree fixing is the most commonly used system on modern engines. The serrations which form the fir tree are very accurately machined to ensure that the enormous centrifugal load is shared equally between them. The blade is free in the serrations while the engine is not rotating, but during operation the centrifugal force imposed holds it firmly in place. The turbine is a very efficient mechanical device. Nevertheless, it does suffer losses during its operation. On average, the energy loss in the turbine is about 8%. This 8% is comprised of approximately 3.5% from aerodynamic losses in the turbine blades and 1.5% aerodynamic losses in the nozzle guide vanes. The rest is divided fairly equally between gas leakage over the blade tips and exhaust system losses. The maximum temperature that the turbine assembly can withstand limits the thrust or power available. Exceeding the maximum turbine temperature will cause irreparable damage to the engine. Therefore, it's imperative that the turbine temperature is monitored closely. The temperature of the turbine is measured by thermocouples, which are placed in the gas flow somewhere in the turbine assembly, typically after the high or low pressure turbine. The temperature measured at this point would be termed the exhaust gas temperature, or EGT. Other terms that are used to represent the value of the gas temperature around the turbine zone are turbine inlet temperature, or TIT, turbine gas temperature, or TGT, jet pipe temperature, or JPT. The jet pipe temperature is so named because of the position of the thermocouples. They are actually placed behind the turbine in the jet pipe itself. In some modern engines, the thermocouple probes are fitted inside selected fixed nozzle guide vanes to enable temperature to be sensed without the probe being battered by the high-velocity gas flow. As the engine is accelerated to produce more thrust or more shaft horsepower, the exhaust gas temperature will increase in proportion with the extra fuel flow, and vice versa. That completes the lesson on turbines.